This is lesson 12.4. We're going to continue where we left off from 12.3, looking at the pendulum. And the pendulum is an interesting question because it could swing forever, ever so subtly, but eventually it has to stop, right? And this really represents an infinite series pretty well. You may not think that, okay, infinite forever, and series meaning summing up. How can we sum up something that goes forever? Well, it has to go forever towards zero. That's the idea. And this pendulum is an excellent example of that. We have an R value of 0.97, and we have an A sub 1 of 120. And I believe on the last question it asked you for the first 12 swings or the first 14, I don't remember. But we could sum up the first 12. A sub 1 is 120. You would take 1 minus 0.97 to the 12th, all over 1 minus 0.97. All right, again, I think it's easier to move that denominator underneath the A sub 1. So A 7, or the sum of the first 12 terms is 120 divided by 0.03 times 1 minus 0.97 to the 12th. All right, and if we take 120 divided by 0.03, we end up with 4,000. And when we multiply it by that remainder, answer times 1 minus 0.97 to the 12th, well, we only end up back at 1,224.6. So in 12 swings, back and forth, it goes about 1,200 total centimeters, I believe this was. Okay, well, what happens if we just let that swing forever? All right, what happens if we change that sum not to the sum of 12, but what if we do like a sum of infinity? All right, let's just say, for example, we could plug infinity in. Well, it's still the same 120, and we're going to end up dividing by 1 minus 0.97. But the only thing that changes here is the 0.97 isn't to the 12th anymore, it's to the infinity. All right, well, we can't actually plug infinity in, but the idea remains. What is 0.97 to infinity? Well, let's write it as a fraction. 97 over 100 to infinity, okay, which we could distribute. If infinity exists, why can't we distribute it? So we have 97 to the infinity over 100 to the infinity. Well, neither of those things actually make sense, but we can begin to see that no matter how big 97 to the infinity gets, okay, the denominator is always going to be bigger. So this is eventually going to head to 0. Well, which means if this goes to 0, 1 minus 0 just goes to 1, and we don't need to multiply. And the sum, if you let this pendulum swing forever, would just be 4,000. And that right there, A sub 1 over 1 minus R, is the sum if you let the pendulum swing forever, if you let the series go forever. But of course, it has to approach 0. If it doesn't approach 0, this sum doesn't hold true. A swing is another example. A person is given one push on a swing. On the first swing, the person travels a total of 4 feet. Each successive swing, the person travels 75% of the distance. What's the total distance the person swings? Well, they're not going to sit there forever, but eventually their swings will become so small they're not measurable. They're not going to kick, they're not going to push, they're not going to add any momentum, they're just simply going to enjoy the ride. So we can use our infinite sum formula. A sub 1 over 1 minus R, 4 over 1 minus 0.75, which is 4 over 0.25. The sum is 16 feet. Not a very long ride, but certainly something that we can simulate with a swing. Now, of course, no one would sit on the swing for an infinite amount of time, but we know that as you sit there, your swings become closer to zero. Here is that infinite sum. Go ahead and write it down now and read that key. You must have an R value between 1 and -1. All right, which means this kind of tells us this is going towards 0. You won't be able to sum something up if it's doubling. It just doesn't work. All right, it has to be approaching 0. It has to be a fraction that is between 1 and -1. All right, it still can approach 0 if it's alternating. That's fine. All right, so I've got a couple practice problems for you here. Remember, always we're going to check to see if R is less than, between 1 and -1. All right, so first identify R. That's probably the most important thing. We do need a sub 1, but R is where we need to start. So R in this situation is 0.6. Our a sub 1 is just 6. All right, that fits. I can find the sum of this. The first term is 6 divided by 1 minus 0.6. So it's 6 divided by 0.4. The sum of this infinite series, once you add everything up towards infinity, it would total up to 15. Number 2, we have a alternating series. I can see that because we are changing signs. Again, the easy way to find the R value is to take one term and divide by the previous term. I think the easiest two terms is going to be this. So we've got 2/3. Divide that by 1. Well, 2/3 divided by 1 is just 2/3. And actually, that's a negative 2/3. So our R value is going to be negative. So R is a negative 2/3. A sub 1 is just 1 in this situation. We're okay. We can use this sum. Or we can sum this infinite series. So the sum will be 1 divided by 1 minus a negative 2/3, which is going to be 1 divided by 1 minus 2/3 is going to be 1 minus negative 2/3. This is going to turn into a positive 1 plus 2/3. So this is 3/3. That would be 5/3. Dividing is the same as multiplying by reciprocal, so we can turn this into 1 times 3/5, and 1 times 3/5 is just 3/5. Sum is 3/5. The final example I have for you here is also another alternating. We can very easily find the sum. We can find R value by looking and seeing, okay, we're multiplying by a -2, -2, -2. R equals -2. Okay, well, right there, this is not approaching 0. Even though it's alternating positive, positive, negative, it is getting bigger, too big to ever sum. All right, each term after this would add something that we just could not actually calculate. So the sum does not exist. Does not exist. All right, I've got a checkpoint for you. I'm going to have you do these problems on the quiz at the end of this lesson. Here's the last question that I want to end with here. Looking at a bouncing ball. A bouncing ball is dropped from a height of 40 feet. So let's say you're on a building and you are going to drop a ball. The ball is going to be dropped. And on the first fall, it bounces 40 feet. Each time it hits the ground, it bounces 3/4 of its previous height. So it hits the ground and it comes up. 3/4 of that is 30. But then what's different about the pendulum is that it also goes down 30. And the ball would not actually be bouncing out like this. The ball would technically probably be bouncing straight up and down, but it's easier to draw this. So now, again, we've got a bounce of 30 now, original height, and it's going to travel 3/4 of that. So it will travel up and then down again, 22.5 and then 22.5. And then it will travel up again. I'll multiply that number by 3/4 one more time here, and it will travel up 16.875, and then it will travel down 16.875. And eventually this pattern would continue until the bounces are really not happening at all. It's not getting off the ground at all. So how do we write this as a geometric series? Well, the one thing that I'm going to tell you is that we want to take this into account, but we want to ignore it. It just doesn't fit the pattern. All right, that 40, because it doesn't have this side of the 40, right? It didn't get thrown up 40, it got dropped from 40. So it doesn't have both. All right, it doesn't have both. So what we can do, we'll ignore that. All right, we'll just have to add that in later. What I do see is that I've got a 30 and a 30, so the total bounce or the total distance on this bounce was 60. I've got a 22.5 and a 22.5. The total bounce on this was 45. 16.8 and 16.8. This was 33.75. So each bounce is following that pattern. It's that 3/4 still. It's just that we need to use this number because we don't have a way to sum. We can't sum 30 plus 30 plus 22.5 plus 22.5. There's not a pattern here, right? That's not geometric. We're not multiplying by same thing here. We're skipping a term, and we don't want to look at that. So we're going to sum 60 plus 45 plus 33.75, so on and so on. So we'll just use our infinite sum. It's our value we know is 3/4. The a sub 1 that we're going to use is 60. All right, we need to make special note here that we will be adding that 40 in at the end once we sum the infinite part. So I'll take the sum is equal to 60 divided by 1 minus 3/4, which is 60 over 1/4. 60 times 4 is going to be 240. So the sum is 240 feet. That's for the infinite part that we could sum together. We also need to add in the 40 for a total now of 280 feet.